Okay, here we are, 8-3, day 2. And it's still these maximum and minimum problems. I'm only going to do one here today, and then I can't do one of everything. It's impossible, but you just got to try and think and get started. So I'll just do one. We're going to create a box from an 8-inch by 12-inch piece of cardboard. By cutting a square from each corner. And turning up the sides. We're going to create this box that has a maximum volume. We want to maximize volume. Okay, so just as a visual, this is a regular sheet of paper where I've got a square, well, not exactly precise, but a square cut from each corner. And you can see once you cut it out, you fold up the sides, and you can create a nice little box. And we want this box to hold maximum volume. So, draw yourself a picture. And what I know about this is it's an 8 by 12. And then I'm going to be cutting out a square from each corner. That's going to be cut out and gone. Cut out and gone. Gone. And gone. Okay, that is a square piece. So I don't know the dimensions yet, so I'll call that an X by X piece. Okay, so I've got, when I fold it up, I've got an open top box, and it's a rectangular prism, and I want to maximize volume. Well, the volume of a prism, rectangular prism, is just length times width times height. Well, if I go back to this box, this is going to be the length of my box from here to here. Well, remember, the whole thing was 12, and I cut out this piece of the square and this piece of the square. Each of those has a length of X. So what's left in the middle here is going to be 12 minus that and minus that. So 12 minus 2X. Using that same reasoning along the side here was 8 from corner to corner. But now I'm only left with this chunk in the middle. I'm taking off this part and this part, so that's going to be 8 minus 2X. And if you think about the height I get when I fold up those sides, this distance here is what's going to be standing up in the air. So my height is going to be equal to X. So my volume equation is going to be the quantity 12 minus 2X times the 8 minus 2X times the height of X. So, because I only have X's in here, I don't need a second equation. I'm ready to go. So before I do derivative, though, otherwise I'd have to do it with the 3 parts to it, with the chain rule with 3 parts. That's kind of long. I think I'm going to take the time to FOIL this out and distribute in the X so it's a little bit easier. So I'm not going to do derivative yet. I'm going to FOIL these two together. So I'll have 12 times 8 is 96 minus 24X. Inside here, minus 16X. And then a plus 4X squared. And I've got that whole thing still times X. So let me combine the X's here, and then I'll distribute the X in. I've got 96 minus a negative 24 minus 16 more is minus 40X plus 4X squared. And I've got all that times x. So if I distribute the x into all three parts, my volume equation is 96x minus 40x squared plus 4x cubed. Now I want to find the derivative so I can find the critical point where this is hopefully a maximum. So I'm ready for derivative. Derivative of 96x is 96 minus 80x. And here's a plus 12x squared. Okay, I want this to equal 0. Okay, I've got a quadratic equation to solve. You're going to use your quadratic formula. I don't have my calculator handy, but you know it's on your A111 quad. Put in your A. Remember, your A comes from the x squared, that's a 12. Your B comes from the x, that's a negative 80. And your C is the constant term. So put that into your A111 quad. You will get x equals 0.314, and you will get a second answer. X equals 6.315. Okay, I forgot to do the domain thing because you don't always need it. I need it right now. Which one is either of these out of the domain? Well, if I think about it, can I cut a 6-inch square from each corner? Is this possible? Well, I only had 8 inches on the short side. There isn't 6 inches from each corner that I can cut out. So this would be out of my domain. So that means I am hoping that the 0.314 is a maximum, and I'm not going to be able to tell until I do the second derivative test. The second derivative at 0.314. So second derivative will come right here. So that will be a 96 minus 40. Oops, derivative of 96 is 0, sorry. Derivative of 96, oh wait, where am I at? Right here. Yeah, derivative of 96 is 0. Then derivative here will be minus 80. And then I'll have a plus 24x. Okay, if I plug in the 0.314 here, and I work this out, this will come out negative, which means concave down, which makes this a maximum at 0.314. And that's what I was looking for, to maximize the volume. So I didn't even ask you, but I wanted the dimensions of the box, or no, what did I want? Let's give the dimensions of the box. So if the height is 0.314, I just have to plug in the length will be 12 minus 2 times 0.314. I don't have a calculator handy, so I can't work that out. The width, 8 minus 2 times 0.314. The height is just equal to the x, 0.314. And if it asks for volume, you can just multiply all three of those together. Length times width times height. Sorry I didn't have my calculator handy to do that, but that's okay. I think you get the idea. Okay, one more. Let's see, is this one today or the next one? Let me take a look real quick here. Equations. Let's see. No. No. Yep, there's one. Okay, one more. I thought I lied. It's a quick one. Semi-quick. Okay. Example 2. We want to find the maximum area of the rectangle under the curve y equals 2e to the negative x squared. Well, if you look at this graph, it looks like this. And our goal, that was supposed to be right down the center there. Our goal is to put a rectangle underneath here of maximum area. So like this. Just pretend that that's right down the middle there. I gotta draw it. Okay, I could draw this rectangle. I could make it a taller, skinnier rectangle. Or I could make it a real low rectangle. It's which rectangle is going to have the maximum area. Well, okay, so that's the equation, y equals 2e to the negative x squared. Alright, so we're trying to maximize the area of the rectangle. So I need to know the dimensions of the rectangle. So I know the distance from the origin over, this is x, so that makes the whole bottom side of my rectangle a length of 2x. And the height of my rectangle is my y value that's on the curve. That's the y. So the area of my rectangle is going to be 2x multiplied by y. Well, I can put the y in terms of x because I've got the equation that's giving me this y value. So in place of y, I'm going to substitute in the equation in terms of x. So that'll be times 2e to the negative x squared. Simplifying here, I am allowed to multiply everything's multiplied out here. 2 times x times 2 times e to the negative x squared. So what I actually have is 4x e to the negative x squared. Okay, so now I'm ready for derivative. A prime. So hopefully you're picking up. I've got a product rule here. I've got the 4x is my u, and then the e term is my v. So the derivative of 4x is the 4 multiplied by the v plus, keep the first term the same, multiply by the derivative here. The derivative here is itself, multiplied by the derivative of the exponent, which is going to give me a negative 2x. So just simplifying this term, 4e to the negative x squared. Here I will have a minus 8x squared e to the negative x squared. Okay, this is actually solvable if I factor, because I want to let this equal 0. If I factor this, I can take out a 4 and an e to the negative x squared out of both baskets. That leaves a 1 in this basket minus, let's see, I had a 8, I took out a 4, dividing it out, that leaves a 2, x squared, and then the e is out there. So I've got two things multiplied together to give me 0, so that means 4e to the negative x squared equals 0, or 1 minus 2x squared equals 0. Think about this negative exponent here. This is 4 over e to the x squared. Well, the only thing that's going to make this come out 0 is if the numerator is 0. Well, there's nothing up here to make it 0. So there is no solution on this one. Over here, I can subtract 1 and divide by negative 2. So I will take the square root of 1/2, which is about